Right now, you are surrounded by dying stars, not dying loosely, but in the most absolute sense physics allows, burning through a finite fuel supply that will never once be refilled, in a universe actively pulling every neighboring galaxy, every source of warmth, across a horizon they can never return from. Scientists have confirmed that approximately 90 to 95% of what you can see tonight is already beyond the point of contact, moving away faster than light can follow, and that number grows every passing year. The universe is not waiting for its stars to die. It is already dismantling the very conditions that made them possible. Tonight, we follow that process all the way to its end. The last star, the last light, the silence that follows forever. If this kind of journey is what you come here for, slow, deep, and genuinely illuminating, hitting like and subscribing is the quiet way of saying so, and it means more than you might think. Pull your blanket closer and let yourself settle in. In 3, 2, 1, liftoff. There is a moment, if you have ever stood far enough from city lights, when the sheer weight of the sky above you stops being beautiful and starts being something else entirely. The band of the Milky Way stretches from one horizon to the other, not like a painting but like a fact, dense and indifferent and impossibly old. You cannot count what you are looking at. You cannot even properly see it. What reaches your eyes is a compressed fraction of something that extends in every direction for 100,000 light years, an object so large that the light leaving its far edge tonight will not reach its own near edge for 100,000 years. And inside that structure, at this moment, something on the order of 400 billion individual stars are burning. Each one is a nuclear furnace. Each one is consuming a fuel supply that will run out. Each one is, in the truest sense of the word, dying, burning through what it was given at the beginning, with no mechanism by which it can be replenished. This is the Stelliferous Era. Astronomers Fred Adams and Gregory Laughlin named it. The word stelliferous means simply bearing stars. It describes the current phase of the universe's history, the period stretching from roughly 100 million years after the Big Bang, when the first stars ignited out of primordial hydrogen and helium, through to approximately 100 trillion years from now, when the last red dwarf in the observable universe will finally exhaust its fuel and go dark. 100 trillion years. It sounds like infinity. In fact, it is nothing of the sort. It is a window. A cosmically generous window, an almost unimaginable span of time from a human perspective, but a window nonetheless. The universe is not always going to look the way it does right now. What you are witnessing when you look at the night sky is not the steady state of the cosmos. It is the peak. It is the middle of a story that had a beginning and will have an ending, and we happen to be living inside the most radiant chapter. To understand what is being lost, you have to first understand what it means for a star to exist at all. Stars do not simply happen. They are the product of violence and patience working together over millions of years. A star begins as a cloud, a vast, diffuse, cold reservoir of mostly hydrogen gas, drifting through interstellar space with so little density that a cubic centimeter of it contains fewer molecules than the best vacuum humanity has ever produced in a laboratory on Earth. These clouds drift for millions of years undisturbed. Then something disturbs them, a shockwave from a nearby supernova, a gravitational nudge from a passing galaxy, a random density fluctuation that reaches a critical threshold. Whatever the cause, the cloud begins to collapse inward under its own gravity. It fragments as it falls, each fragment pulling itself tighter, heating as gravitational potential energy converts into thermal energy. The fragment glows. It radiates. It is now a protostar, an object that is hot and bright for the wrong reasons, not yet powered by fusion, still just collapsing. This collapsing phase lasts millions of years. The gas contracts. The temperature at the core climbs. Pressure builds. When the temperature at the heart of the collapsing fragment reaches approximately 18 million degrees Fahrenheit, something remarkable happens. The nuclei of hydrogen atoms, single protons, begin moving fast enough to overcome the electromagnetic repulsion that normally keeps them apart. They collide, they fuse. 2 protons become a deuterium nucleus. Further fusion steps follow. 4 protons become a helium nucleus, and in the process, a tiny fraction of mass is converted directly into energy according to the most famous equation in physics. Energy equals mass times the speed of light squared. The energy released in this process flows outward as radiation and thermal pressure, pushing back against the inward crush of gravity. The 2 forces reach an equilibrium. The collapse stops, the star is born. What has just been described is not merely a beginning. It is the starting of a clock. From the moment a star ignites, it is living on borrowed time, burning through the hydrogen in its core with no way to replace it. The question from that first ignition onward is not whether the fuel will run out, but only how long it will take. And the answer to that question, it turns out, depends entirely on the mass of the star, because mass determines everything about a star's life: how bright it burns, how long it lasts, and what kind of corpse it leaves behind. This relationship between mass and luminosity is not intuitive. You might expect bigger stars to last longer simply because they have more fuel, but this is exactly wrong. The nuclear furnaces inside massive stars burn at far higher temperatures than those inside smaller stars, and higher temperature means higher reaction rates, which means the fuel is consumed with catastrophic speed. A star with 20 times the mass of the Sun does not burn 20 times longer than the Sun. It burns roughly 20 times brighter per unit of mass, and as a result, it exhausts its nuclear fuel in just a few million years, a cosmological eye blink compared to the Sun's expected 10 billion year lifespan. Somewhere in our galaxy right now, there are blue supergiant stars blazing at hundreds of thousands of times the Sun's luminosity, and they have only been alive for 3 or 4 million years, and they will be dead before humanity's civilization has had time to double its present age. They are the mayflies of the cosmos. Spectacular, brief, and absolutely destined to vanish before anything around them has barely noticed they were there. Betelgeuse, the enormous red supergiant that dominates the constellation Orion, is a perfect example of this compressed timeline in action. It has a mass somewhere between 8 and 20 times that of our Sun, and it has already exhausted the hydrogen in its core and moved on to fusing heavier elements, working its way down through the periodic table in ever shorter burning stages as each fuel is consumed. Helium burns for roughly 1 million years, then carbon for hundreds of years, then neon for a year or so, then oxygen for a few months, then silicon for perhaps a single day. The ion that fusion eventually produces cannot release energy when fused. It absorbs energy instead, and when a sufficient iron core accumulates, the entire structure of the star collapses in less than a second, and Betelgeuse will explode in a supernova visible from Earth, even in daylight. That supernova will scatter the products of Betelgeuse's nuclear furnace across the surrounding interstellar medium, enriching the next generation of stars and planets with the heavy elements that were forged inside it, but the star itself will be gone. What remains will be either a neutron star an object roughly 20 kilometers across, packing the mass of the Sun into a sphere smaller than a city, or, if enough mass collapses, a black hole. Neither of these things is a star, neither of them burns, neither of them will ever produce light through nuclear fusion again. The fate of Betelgeuse captures something essential about the most massive stars in the universe. They are the universe's most spectacular contributors and its most efficient consumers simultaneously. They pour out energy at rates that make them visible across galactic distances, and they synthesize every heavy element in existence, from carbon to iron and beyond in the supernova blast itself. The elements beyond iron on the periodic table, forged in those final violent seconds. Without the deaths of massive stars, there would be no rocky planets, no oceans, no organic chemistry, no life of any kind anywhere in the universe. The iron in your blood was forged in the core of a star that exploded billions of years ago. The calcium in your bones was scattered across space in a supernova shockwave before our solar system existed. The silicon in the computer chips that encode everything you have ever read was produced in a stellar furnace that burned out long before the sun was born. You are made of what massive stars left behind, and those stars are gone. Massive stars, for all their drama, represent only a small fraction of the total stellar population. The overwhelming majority of the stars in the universe, somewhere between 70 and 80% of all stars by count, are not blue giants or supergiants or anything close to the spectacle of Betelgeuse. They are dim, red, barely visible to the naked eye even in our own cosmic neighborhood, patiently glowing with a fraction of a percent of the sun's luminosity, and they will still be alive when the universe is orders of magnitude older than it is now. These are red dwarfs, the quiet majority, the universe's longest-lived stars, and understanding them is essential to understanding what the Stelliferous Era actually looks like from the inside. Because the era of starlight is not evenly distributed across time, it is weighted almost entirely toward the patient end. The nearest star to our solar system is a red dwarf. Proxima Centauri, 4¼ light-years away, burns at roughly 0.1% of the sun's luminosity. It is so dim that despite being our nearest stellar neighbor, it cannot be seen with the naked eye from Earth. Its surface temperature hovers somewhere around 6,500 degrees Fahrenheit, compared to the sun's roughly 10,000 degrees Fahrenheit at the photosphere, and it has a mass of only approximately 1/8 of the sun's. But that small mass, combined with an internal structure that the sun does not share, gives Proxima Centauri an extraordinary advantage in the business of survival. The sun burns hydrogen only in its core, roughly the innermost 10% of its volume, because the rest of the star is hot enough that convective mixing does not reach all the way down to pull fresh hydrogen in from the burst. Outer layers. The core hydrogen runs out in roughly 10 billion years, and then the sun begins its expansion into a red giant, regardless of the fact that most of the hydrogen in its outer layers has never been touched. The vast majority of the sun's hydrogen is essentially unreachable by the nuclear furnace at its heart. Red dwarfs work differently. Their low mass means their internal pressures and temperatures are low enough that convection carries material all the way from the surface to the core and back again, continuously mixing the entire star from inside to outside. Every atom of hydrogen in a red dwarf is, in principle, available to the nuclear furnace at its center. Nothing is left unburned. A red dwarf, with 1/10 the mass of the sun, has roughly 10 times less hydrogen to start with than the sun does, but it burns that hydrogen at a rate so slow, so vastly slower, that the total lifetime works out to somewhere between 6 and 10 trillion years. The universe is currently 13.8 billion years old. A trillion years is roughly 72 times the current age of the universe. The dimmest red dwarfs in the cosmos have barely started their lives. They are newborns by any meaningful cosmic measure, and they will still be burning when the universe is 70 times older than it is right now. This is the shape of the Stelliferous Era, blazing at its peak right now, in this cosmological instant, with massive stars already dead, medium stars like the Sun in their Middle Ages, and the patient red dwarfs still in their infancy. The current rate of star formation is, by historical standards, actually declining from a peak that occurred roughly 10 billion years ago, when the universe's supply of free hydrogen gas was at its most abundant, and conditions for stellar nurseries were at their most favorable. We are not at the beginning of star formation. We are at the tail end of it. The great era of galaxy building and new star ignition has already passed. What surrounds us now is a cosmos full of stars that are already burning, some in their first few million years, most in their long Middle Ages, some in their final billion years, and a slowly diminishing supply of raw material from which new stars can be born. Every molecular cloud that collapses into a new star removes that gas permanently from the available reservoir, converting it into stellar matter that will eventually be locked into a white dwarf, or neutron star, or black hole, and never again become a fresh cloud capable of forming a new star. The universe's gas budget is finite. The total mass of hydrogen available for star formation has been declining since the Big Bang, and it continues to decline with every new star that forms. Star formation is not a renewable process. Each star that ignites represents a permanent expenditure against a supply that will not be refilled. The same cosmic process that produces the light also consumes the raw material that produces the light, and there is no mechanism in physics by which new hydrogen can be manufactured to replace what is burned. The closest thing to a cyclical element in stellar evolution is the fact that massive stars, when they explode as supernovae, scatter hydrogen and helium back into the interstellar medium, along with the heavier elements they have synthesized. But this recycling is imperfect and lossy in the worst thermodynamic sense. Not all the hydrogen goes back into circulation. Some is locked into the remnant neutron star or black hole. Some is consumed by the supernova explosion itself. Some disperses into the intergalactic medium and never falls back into any galaxy. And crucially, the heavier elements mixed into the recycled material change the chemistry of the next generation of star-forming clouds, enriching them with metals. The astronomers' term for any element heavier than helium, which subtly changes how they collapse and what kinds of stars they produce. The universe grows progressively more metal-rich with each stellar generation, which is a reminder that the cosmos is not static. It is changing chemically and structurally with each round of stellar birth and death, and the direction of that change is not toward renewal, but toward depletion and transformation. Consider what the night sky would have looked like 300 million years after the Big Bang, during the epoch of reionization, when the first generation of massive stars, population 3 stars, as astronomers call them, were blazing at enormities of luminosity that modern stars cannot match. These ancient stars formed from gas that was almost pure hydrogen and helium with essentially no metals at all, and they may have reached masses of hundreds of times the Sun's, far exceeding anything we observe today, burning out in less than 1 million years each. They were the universe's first lights and its most extravagant waste. Their deaths scattered metals across the cosmos for the first time, seeding the conditions for smaller, longer-lived, metal-enriched stars to follow. But those population 3 stars themselves are utterly gone. Not a single one survives. Every one of them exhausted its fuel billions of years ago, collapsed and exploded. The universe has been accumulating stellar corpses for more than 13 billion years now, and the pile grows with every passing century. This is the hidden truth of the Stelliferous Era. It is not a stable condition. It is a slowly decelerating burn. The universe formed stars at the highest rate roughly 10 billion years ago, during what cosmologists call cosmic noon. Since then, the star formation rate has declined. Molecular clouds collapse more slowly now than they did then. The universe's gas reservoir, while not exhausted, is significantly depleted from its earlier abundance. The pool of material available to form the next generation of stars is shrinking. And even as new stars are born, older ones are dying, and the balance between formation and extinction has shifted progressively toward extinction. We are past the midpoint. The universe is already on the descending side of its stellar life cycle, and we are witnessing what that descent looks like from the inside, surrounded by billions of stars. Yes, but surrounded by billions of stars in which the mathematics of finite fuel is inexorably ticking. What makes this observation especially striking is the range of timescales involved. On a human timescale, nothing about the night sky changes. The stars Galileo observed through his first telescope 416 years ago look identical tonight. The constellation patterns that ancient Babylonians used for navigation more than 3,000 years ago are essentially unchanged. From inside a human life, the universe appears static, permanent, unchangeable, but this appearance is entirely an artifact of the mismatch between human timescales and cosmic ones. The sun has not noticeably changed in recorded human history, but it was significantly dimmer 4 billion years ago when life first appeared on Earth, and it will be noticeably brighter in another billion years, bright enough to boil the oceans and render the surface of this planet uninhabitable, regardless of what humanity does or does not do to address it. In the meantime, the stars are changing. They are aging. They are burning down their fuel. The stillness of the night sky is not evidence of permanence. It is evidence of the extraordinary gap between human perception and cosmic reality. There is something almost disorienting about the fact that we cannot see the change happening around us. We live embedded in a process, the Stelliferous Era, so vast and slow that its motion is invisible to any individual observer. The oldest person who has ever lived has witnessed less than 100 years of cosmic history. The universe has been in the Stelliferous Era for 13 billion years. We have seen nothing of the arc. We have caught a single frame of a film that runs for 100 trillion years, and that frame happens to show the universe full of burning stars, and it would be easy, dangerously easy, to mistake that frame for the whole story. The sky overhead tonight looks essentially identical to the sky that ancient astronomers charted more than 2,000 years ago. The same stars hold the same relative positions. The same galactic band stretches across the same arc of darkness. From inside a human lifetime, the universe does not appear to be dying. It appears to be the permanent state of things. This is one of the most powerful illusions in all of science. The cosmos presenting itself as stable and eternal precisely because it operates on timescales too long for any observer embedded within it to perceive its motion. But the motion is real, and it shows up in ways that are measurable even from inside our brief observational window, if you know what to look for. Astronomers can observe the star formation rate in galaxies at different distances, which means galaxies at different ages, because the farther away a galaxy is, the older the light we receive from it. And the older the light, the further back in time we are looking. Galaxy surveys have established conclusively that the universe was forming stars at a dramatically higher rate several billion years ago than it is today. Observations of galaxies at redshifts corresponding to roughly 10 billion years ago reveal a cosmos ablaze with new stellar formation, galaxy collisions driving starburst activity, molecular clouds collapsing at rates that dwarf anything we observe in the nearby universe now. The universe was more productive then, and it has been winding down since. That decline is not speculative. It is directly observed, measured across billions of light years and billions of years of cosmic history, and the trend lines are unambiguous. The same observation that reveals the declining star formation rate also reveals something about what the universe looks like at the largest scales and the deepest distances. When astronomers peer at extremely remote galaxies, objects so distant that their light was emitted only a billion years or so after the Big Bang, they observe galaxies that are irregular, lumpy, actively colliding, saturated with star formation, and physically smaller than modern galaxies of comparable mass. These are the young galaxies, the ancestors of the quiet spirals and ellipticals we observe in the nearby universe, and they are forming stars at rates that modern galaxies simply cannot match. The modern universe, the universe we inhabit right now, is older and quieter and more settled. The great upheavals of galaxy formation, the mergers and collisions and torrential starbursts that characterized the first few billion years, have mostly subsided in our cosmic neighborhood. What we see around us is the relatively calm middle period of a long story, not its beginning and not its end, but a moment recognizable as the tail end of the universe's most productive phase and the beginning of its long, slow winding down. The sun itself encodes this history. The sun is a population one star, meaning it formed from gas that had already been enriched by multiple generations of stellar nucleosynthesis before our solar system began assembling from its birth cloud 4.5 billion years ago. The heavy elements in the earth, the iron in the core, the silicon in the mantle, the oxygen in the atmosphere, the carbon in every living cell, were manufactured in the nuclear furnaces of stars that lived and died before our sun existed. We are third-generation stellar material at minimum, likely further still. Each generation of stars burns some hydrogen, makes some heavier elements, and dies, leaving those heavy elements available for the next generation's molecular clouds. But each generation also permanently converts some hydrogen into stellar remnants, white dwarfs, neutron stars, black holes that will never contribute to star formation again. The universe's hydrogen inventory is a one-way ledger, and the sun, by forming at all, drew down from that ledger. The sun's formation was the universe's investment of 4.5 billion years worth of raw material into what will eventually become one more white dwarf, cooling in the dark. To get a sense of the time scales involved in the Stelliferous Era's overall arc, consider the following sequence. The first stars in the universe ignited approximately 100 million years after the Big Bang, when the first molecular clouds of hydrogen and helium had cooled and collapsed sufficiently to begin nuclear burning. Those early massive stars lived for only a few million years before dying in supernovae. Smaller stars followed, living longer, enriching the gas supply with each death. Galaxy formation proceeded, driven by the gravitational attraction of dark matter halos, pulling gas into concentrated regions. By about 3 billion years after the Big Bang, the universe had established recognizable large-scale structure, with filaments and voids and galaxy clusters forming the cosmic web. By roughly 10 billion years after the Big Bang, the universe's star formation rate reached its peak and began declining. By 10 billion years after the Big Bang, 3.8 billion years ago, the solar system was born from a cloud of enriched gas in one of the Milky Way's spiral arms. And now, at 13.8 billion years after the Big Bang, we find ourselves at a moment when the rate of star formation is roughly 10 times lower than it was at cosmic noon, and falling still. The Stelliferous Era extends from the formation of the first stars to the extinction of the last red dwarf, a span of approximately 100 trillion years. We are currently 13.8 billion years into that span. To put it in a proportion, if the entire Stelliferous Era were compressed into a single calendar year, the current moment, all of human history, all of recorded civilization, all of the universe as we know it from the Big Bang to today, would fall on the very first hour of January 1st. We are that early in the overall arc. The vast majority of the Stelliferous Era, measured in raw time, lies ahead of us. The red dwarfs have not yet reached their middle age. The last star will not extinguish itself for another approximately 100 trillion years. And yet, this abundance of remaining time does not change the fundamental shape of the story. The Stelliferous Era is not a flat plateau of uniform stellar activity stretching 100 trillion years into the future. It is a curve that peaked billions of years ago and is now descending a curve on which the massive stars are already gone, the medium stars are dying or near the end of their main sequences, and the remaining abundance of light is being maintained almost entirely by the patience of red dwarfs. The universe has already used up its most spectacular material. The blue giants, the supergiants, the population, 3 stars, these are memories. What the Stelliferous Era has remaining is its patient reserve, its long, slow, dim tail, the hundreds of trillions of years during which the last red dwarfs will quietly burn in an increasingly dark and increasingly isolated cosmos, one by one, separated by expanding space from the remnants of everything that burned before them, surrounded by cold white dwarfs and neutron stars and black holes, illuminating nothing except the immediate darkness around themselves. This is the shape of what the Stelliferous Era actually delivers over its full span, an opening act of spectacular brilliance that has already mostly passed, a middle period we are now inhabiting that is quieter but still richly populated, and a closing act of extraordinary duration but vanishing luminosity in which the universe's remaining starlight slowly concentrates into the coldest, dimmest, most patient burning objects in existence. And then, one by one, those too go dark. Consider, too, what it means for the Stelliferous Era to be the universe's only era of this kind. As far as current physics can determine, there is no second act. The universe will not eventually stop expanding, cool down, and then begin collapsing, at least not in any model consistent with the confirmed presence of dark energy maintaining or accelerating cosmic expansion. The universe will not cycle back to a new Big Bang that replenishes the hydrogen supply and starts the whole process over. There is no evidence for any mechanism that would refill the gas reservoir, reignite extinguished remnants, or reassemble the conditions for a second Stelliferous Era. What happens once is all that happens. The stars burn through what was given at the beginning, and when it is gone, The universe enters a state without stars and stays there. There are no reruns. The light that fills the cosmos right now, all of it, from every galaxy, every nebula, every distant quasar, still visible across billions of light years, is part of one single era of stellar burning that will eventually end and not be followed by another. This is the context that gives the Stelliferous Era its emotional weight, if you are willing to feel it. The weight is not grief, it is recognition. Recognition that the brightness around us is specific, that it is bounded, and that the physics responsible for it has already begun the process of consuming it. The light pouring down on Earth right now from the Milky Way's 400 billion stars is not the light of an eternal condition. It is the light of a stage, the middle stage, the bright stage, the stelliferous stage, and it will not last. The hydrogen supply built into the universe at the Big Bang will continue to diminish. The rate at which new stars form will continue to fall. The stars that are alive right now will continue to age and eventually extinguish themselves in the varied ways their masses dictate. And there is nothing in the physics of the cosmos that creates new hydrogen to replace what is consumed. No mechanism that restarts the fusion clock when it runs to zero. No reset button. No renewal. The Stelliferous Era is burning through its allotment, and when the allotment is gone, the burning stops. The only question is how it stops, how each class of star reaches its end, what it leaves behind, and how completely it severs its connection to the universe it inhabited. That question turns out to have a far more intricate and final answer than the simple phrase stellar death suggests, because the mechanics of how stars die determine not just when the lights go out, but the specific shape of the darkness that follows. Every star in the universe will die, but not every star dies the same way, and the differences matter enormously, not just as a matter of scientific classification, but as a matter of what the death actually means for the universe it leaves behind. A star's death is not simply the cessation of a light source. It is the production of a specific kind of remnant, and that remnant determines whether anything productive can happen in that star's neighborhood afterward, whether the material it contains can be recycled into something new, whether its end contributes to the next chapter of the universe's story or simply closes a door that will never open again. Understanding the mechanics of stellar death means understanding that the universe's long-term future is not shaped by what its stars do while they live, but by the specific types of objects they leave behind when they die, and that those objects, taken together, paint a picture of a cosmos progressively converting its active, burning material into cold, dark, inert matter that can no longer participate in the processes that make the universe interesting. Begin with the most massive stars, because they go first and they go hardest, and their deaths carry consequences that stretch across thousands of light years. A star with at least 8 times the mass of the Sun, and these objects can run to 20, 50, even 100 times the Sun's mass in extreme cases, lives a life defined by an accelerating series of fuel crises. In the beginning, it burns hydrogen into helium in its core, just as the Sun does. But because the core temperature is so much higher in a massive star, the proton-proton chain that powers the Sun gives way to a faster process called the CNO cycle, in which carbon, nitrogen, and oxygen serve as catalysts that dramatically accelerate hydrogen fusion. The result is that a star of 20 solar masses burns through its core hydrogen in only about 8 million years, roughly 1/1000th the lifetime of the Sun. When the core hydrogen is exhausted, helium begins to burn into carbon and oxygen. When the helium runs out, carbon ignites, then neon, then oxygen, then silicon. Each successive fuel burns faster and produces less energy per reaction, so each burning stage is shorter than the last by orders of magnitude. The hydrogen stage takes millions of years. The helium stage takes 1,000,000. Carbon takes a few centuries. Neon takes a year. Oxygen takes a few months. Silicon takes about a day. Silicon fusion produces iron, and iron is the last thing that can exist at the center of a star, because iron is the most stable nucleus in nature. Fusing iron into anything heavier requires putting energy in rather than getting energy out. Iron does not burn, it accumulates. It piles up in the core of the star, a growing ball of inert dead weight that can contribute nothing to the outward pressure holding the star against its own gravity. For a brief time, perhaps days, perhaps only hours, the iron core grows, drawing iron from the silicon burning shell above it. When the iron core reaches a mass of approximately 1.5 times the mass of the Sun, it crosses a critical threshold known as the Chandrasekhar limit, beyond which electron degeneracy, pressure, the quantum mechanical resistance of electrons to being compressed into the same quantum state, can no longer support it against gravity. At that moment, the core stops supporting itself. It collapses, and what happens in the next few seconds is among the most violent events in the observable universe. The iron core collapses from roughly the size of the Earth, a diameter of about 12,000 kilometers, to a sphere roughly 20 kilometers across in less than a second. The density reached in this collapse is almost incomprehensible. The material in the collapsed core is packed to nuclear density, the same density as an atomic nucleus, roughly 200 million billion grams per cubic centimeter. This is not a metaphor for dense. This is literally the density of the atomic nucleus itself, scaled up to stellar proportions. When the core reaches this density, the collapse stops abruptly because nuclear forces become repulsive at short range, stiffening the equation of state and causing the infalling material to bounce. The bounce sends a shock wave outward through the star. That shock wave, combined with an enormous burst of neutrinos carrying away approximately 99% of the total energy released, tears the entire outer structure of the star apart in a core collapse supernova, one of the most luminous events in the universe, capable of briefly outshining an entire galaxy of hundreds of billions of stars. What remains after the explosion depends on how much mass was left in the collapsed core. If the core mass after collapse falls below approximately 2 to 3 times the mass of the Sun, the result is a neutron star, an object roughly 20 kilometers across, composed almost entirely of neutrons packed to nuclear density, spinning rapidly, sometimes hundreds of times per second, and emitting powerful beams of radiation that sweep through space like a lighthouse. Neutron stars are among the most extreme objects in the universe. A teaspoon of neutron star material would weigh approximately 400 million tons. Their surface gravity is 100 billion times stronger than Earth's. If you dropped a marshmallow onto a neutron star from 1 meter above its surface, it would hit the surface with the kinetic energy of a nuclear weapon. They are extraordinary objects, deeply studied, fascinating to physicists. But they are not stars. They do not fuse. They do not burn. They do not produce energy through nuclear processes. They slowly radiate their residual heat and angular momentum into space over millions of years, cooling and spinning down. Eventually, on timescales of billions to trillions of years, they become dark, cold, inert balls of degenerate neutron matter drifting through space. Former stars, now frozen, contributing nothing. If the core mass after collapse exceeds the maximum that can be supported even by nuclear degeneracy pressure, roughly 2 to 3 solar masses, though the exact upper limit remains an area of active research, the collapse does not stop at neutron star density. It continues, and the result is a black hole, a region of space-time where the curvature is so extreme that not even light can escape. The black hole inherits the mass of the collapsed core, locked behind an event horizon from which nothing returns. The mass is still there. In a sense, it still exerts gravitational attraction on everything around it, but it is inaccessible to the universe in any useful way. No light comes out. No radiation comes out at the scale of the stellar black holes formed this way, except for the extraordinarily faint and slow quantum process known as Hawking radiation, which we will return to later in this video. For all practical purposes, when a massive star collapses to a black hole, that mass is gone from the active universe. It is sequestered behind the event horizon, permanently unavailable for star formation, planet formation, chemistry, or any other process. The universe has consumed part of its own mass budget and gotten nothing useful back in return. The supernova itself scatters the material from the star's outer layers: hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, and the full suite of elements, synthesized in those onion shell burning stages across a sphere of space that can eventually grow to hundreds of light years in diameter. This ejected material is enormously valuable in the cosmic sense. It enriches the interstellar medium with heavy elements. When it sweeps through a molecular cloud, it can trigger a new round of star formation by compressing gas to densities sufficient for gravitational collapse. The supernova remnant is, in this sense, a gift to the next generation. But the gift comes with a cost. Every supernova also locks the mass of the core into a compact remnant, a neutron star or black hole that will never contribute to star formation again. The universe trades part of its active mass for heavy element enrichment with each massive star death. And while that trade is enormously productive in the early and middle stages of the Stelliferous Era, the ledger is always moving in one direction, away from available gas and toward locked-up remnants. Now, consider what happens to stars like the Sun, which make up a substantial fraction of the total stellar population, and whose deaths unfold on timescales orders of magnitude longer than those of massive stars, but whose endings are no less final. The Sun has been fusing hydrogen into helium in its core for approximately 4.5 billion years. It has roughly another 5 billion years of hydrogen fusion remaining before the core supply is exhausted. When that day comes, about 5 billion years from now, the sequence of events that follows is very different from the supernova death of a massive star, but it is equally terminal. When the Sun's core hydrogen is gone, the core, now composed mostly of helium, will begin to contract under its own gravity. The energy released by that contraction will heat a thin shell of hydrogen just outside the core, to the point where it ignites and begins fusing, even though the core itself has stopped. This hydrogen shell burning provides more energy output than the core burning did, and the result is paradoxical. The outer layers of the Sun, pushed by this excess energy, will begin to expand outward. The Sun will grow, slowly at first, then more rapidly. Over hundreds of millions of years, its radius will increase from its current size to something on the order of 200 times its current diameter, large enough to extend beyond the orbit of Mercury, past Venus, and, according to most current stellar models, all the way to the orbit of Earth, or slightly beyond, engulfing our planet as a cinder inside a star that no longer resembles anything you would call the Sun. The surface temperature will drop as the star expands. The same total energy output spread across a much larger surface area gives a cooler surface, and the color will shift from yellow-white to deep red-orange. This is the red giant phase, and for Sun-like stars, it lasts roughly 1 billion years. During the red giant phase, the helium accumulating in the core eventually reaches a temperature and pressure sufficient to ignite. In a Sun-like star, helium ignition happens abruptly and explosively in a process called the helium flash, a detonation in the core that, for a few minutes, releases more energy than the entire Sun produces in its whole main sequence lifetime. Strangely, none of this energy reaches the surface. It is entirely absorbed by the expansion of the stellar layers above the core. From outside, nothing dramatic is observed. The Sun simply begins burning helium more steadily, which stabilizes the star temporarily on what is called the horizontal branch. For roughly 100 million years, the Sun burns helium in its core into carbon and oxygen. But helium is a much less efficient fuel than hydrogen. The energy released per gram burned is lower, and the burning happens faster. And when the helium core is exhausted, the same sequence of expansion begins again, driven now by a double shell structure in which both hydrogen and helium burn in successive shells above a carbon-oxygen core. This second expansion phase is called the asymptotic giant branch, and it is during this phase that the Sun becomes genuinely unstable. On the asymptotic giant branch, a Sun-like star develops what astronomers call thermal pulses, periodic episodes of violent instability driven by alternating ignition of the helium and hydrogen shells, each pulse releasing a burst of energy that drives powerful stellar winds from the surface. The outer layers of the star are not tightly bound at this point. The red giant's tenuous envelope extends to distances where the surface gravity is extremely low, and the pulsations are enough to drive this material outward into space at velocities of 10 to 30 kilometers per second. Over tens of thousands of years, a brief interval by stellar standards, the Sun will shed something between 30 and 40% of its total mass in these winds, expelling it into the surrounding interstellar medium in successive expanding shells that glow brilliantly, ionized by the intense ultraviolet radiation from the increasingly hot and exposed core. This glowing structure is a planetary nebula, and it is one of the most spectacular objects in astronomy. The name is misleading. It has nothing to do with planets. It was applied by early astronomers who, looking through small telescopes, found that these glowing circular objects resembled the disk of a gas giant planet. They are actually the shed outer layers of a dying star, briefly illuminated, briefly visible, and extremely short-lived by cosmic standards. The glowing shell of a typical planetary nebula disperses into the surrounding interstellar medium in approximately 10,000 to 50,000 years, before fading into invisibility. What remains at the center of the planetary nebula after all this mass loss is the exposed core of the former Sun, a white dwarf. This object contains roughly half the Sun's original mass. The half that stayed in the core while the outer half was expelled, compressed into an object roughly the size of the Earth. The diameter is about 12,000 kilometers. The mass is approximately half a solar mass which works out to roughly 10,000 trillion kilograms squeezed into a sphere the size of a planet. The density of white dwarf material is about 1,000,000 times greater than the Sun's average density. A single teaspoon of white dwarf material would weigh approximately several tons on Earth's surface. The star is supported against further collapse, not by nuclear fusion, there is none, but by electron degeneracy, pressure, the same quantum mechanical effect that temporarily supported the core of a massive star before its collapse. But in a white dwarf, this pressure is sufficient because the total mass is below the Chandrasekhar limit. The white dwarf will not collapse further, it will not explode, it will not fuse anything. It will simply sit there, radiating the thermal energy stored in it over billions of years, cooling very slowly from initial surface temperatures that can exceed 180,000 degrees Fahrenheit down toward temperatures where it barely glows at all. This cooling process is extremely slow. The cooling timescale for a white dwarf to drop from its initial blazing temperature to something approaching room temperature is longer than the current age of the universe. No black dwarf. The theoretical endpoint of a fully cooled white dwarf is believed to exist anywhere in the observable cosmos, because not enough time has passed since the first white dwarfs formed for any of them to have cooled completely. Every white dwarf that has ever been created is still radiating some light and heat, still technically visible with the right instruments, still technically contributing something to the energy budget of its local environment. But the direction of that contribution is one way. Every white dwarf is cooling. None of them are getting hotter. None of them will ever reignite. The nuclear fuel that once powered them was exhausted in their red giant phase. What they contain is thermal energy stored heat, and that heat is gradually bleeding away into the surrounding space, irreversibly, with no source to replace it. There is an interesting exception, a brief reprieve written into the physics of binary star systems, where two stars orbit each other closely enough that material can flow between them. If a white dwarf has a companion star that is still actively evolving, still on the main sequence, or swelling into a red giant, the white dwarf's powerful surface gravity can draw material from the companion's outer layers through a stream that falls onto the white dwarf's surface in a process called accretion. As the accreted material builds up on the surface, it is compressed by gravity and heated. If enough hydrogen accumulates and reaches sufficient temperature, it ignites in a runaway fusion reaction on the white dwarf surface, not in the core, which remains degenerate and inert, but on the thin layer of freshly accreted hydrogen sitting atop it. This produces a nova, a sudden brightening of the white dwarf that can increase its luminosity by factors of tens of thousands in a matter of hours or days, before fading over weeks as the accreted fuel is consumed. A nova is not the death of the star. Both the white dwarf and its companion survive. The white dwarf settles back to its previous quiescent cooling, waiting for the next round of accretion to build up enough material for another outburst. A different outcome occurs if enough material accretes onto the white dwarf to push its total mass above the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. If that threshold is reached, electron degeneracy pressure is no longer sufficient to support the star, and carbon ignition begins simultaneously throughout the interior of the white dwarf in a runaway thermonuclear explosion that completely destroys it. This is a Type Ia supernova, not the core collapse supernova of a massive star, but a thermonuclear detonation of a white dwarf that has been pushed over its stability limit. The entire white dwarf is obliterated, leaving no remnant at all. Its mass is expelled into space in an explosion so consistent in its peak luminosity, because it always occurs at approximately the same trigger mass that Type Ia supernovae serve as standard candles. Tools for measuring cosmic distances, and it was precisely through their use as distance markers that astronomers confirmed in the late 1990s that the expansion of the universe is accelerating. These explosions are not just deaths, they are the instruments by which we mapped the fate of the cosmos. But most white dwarfs never reach this fate. They have no companions close enough to supply significant material, or their companions are too small, or the accretion rate never brings them to the Chandrasekhar limit. Most white dwarfs simply cool, and cool, and cool. Over time scales measured in hundreds of billions of years, they will cool from the blazing ultraviolet emitting objects. They start as to dim red glowing objects, to objects that emit primarily in the infrared, to objects too cold to emit any detectable radiation at all. The black dwarf is the predicted final state of a white dwarf that has had enough time to complete this cooling process. It would be an object roughly the size of the Earth, with roughly half the Sun's mass, made primarily of carbon and oxygen nuclei, locked into a crystalline structure by quantum effects, cold to within a few degrees of absolute zero, emitting nothing, a perfect dark cinder. As mentioned, no black dwarfs are thought to exist yet in the universe, because even the oldest white dwarfs, those that formed from the deaths of the first sun-like stars more than 10 billion years ago, have not had enough time to cool completely, but they are coming. As the Stelliferous Era progresses and more sun-like stars exhaust their fuel and become white dwarfs, the population of cooling white dwarfs in the universe will grow, and trillions of years from now, that population will be cooling toward the black dwarf endpoint, one by one, each one taking 100 billion years or more to fully extinguish. Now return to the red dwarfs, because they represent the most numerically dominant population in the universe, and their deaths are the most important for understanding the very end of the Stelliferous Era. Earlier, Part 1 established that red dwarfs burn for trillions of years, far longer than any other class of star. That enormous longevity is real and confirmed, but it comes with a set of consequences for what the deaths of red dwarfs look like and what they mean for the cosmic future. Because red dwarfs are fully convective, their entire interior circulating material continuously through the star, the evolution of a red dwarf is fundamentally different from the evolution of the Sun. As the red dwarf burns hydrogen into helium over trillions of years, the helium produced in the core does not accumulate in a static core mass the way it does in sun-like stars. Instead, it is continuously mixed throughout the entire star by the convective circulation. The star's composition changes very gradually and uniformly from hydrogen-rich toward helium-rich across its entire volume. This means a red dwarf never develops the kind of inert helium core that triggers a sun-like star's red giant expansion. It does not expand dramatically. It does not shed its outer layers into a planetary nebula in the same way. It simply gets gradually brighter and slightly hotter as the helium fraction increases over trillions of years, maintaining almost the same radius throughout its entire lifetime. As the hydrogen supply dwindles toward exhaustion, models suggest the star will transition through a theoretical phase astronomers call the blue dwarf stage. The surface temperature will rise as the composition shifts, moving the star from the cool red end of the stellar temperature spectrum toward the hotter blue-white region. This blue dwarf phase has never been observed in reality, because no red dwarf in the universe has yet lived long enough to reach it. The universe is currently only 13.8 billion years old, and even the oldest red dwarfs have existed for far less than 1 trillion years. The blue dwarf stage is a theoretical prediction from stellar evolution models, confirmed to the degree that our understanding of stellar physics allows, but not yet observationally verified, simply because the universe has not yet had enough time to produce one. Eventually, when the last of the hydrogen is gone, the blue dwarf also runs out of fuel and its core contracts. But unlike a sun-like star, the core that contracts is not massive enough to ignite helium into carbon through the triple alpha process. The red dwarf simply does not get hot enough. Its core contracts settles into electron degeneracy support, and the star becomes a white dwarf composed primarily of helium, not the carbon-oxygen white dwarf produced by sun-like stars, but a helium white dwarf, smaller, slightly different in composition, but equally inert. And from that point, the same slow cooling process applies. Billions and trillions of years of heat bleed. Then, in the deepest future, a black dwarf. This is the full landscape of stellar death. Massive stars ending in supernovae and leaving neutron stars or black holes, remnants that consume, without creating, locked away, or slowly cooling. Sun-like stars ending in planetary nebulae and leaving white dwarfs that cool over hundreds of billions of years. Red dwarfs ending in a slow brightening, transitioning to white dwarfs and cooling over unimaginably long timescales. In every case, the endpoint is the same type of object: cold, dark, inert matter that no longer participates in the nuclear cycle that makes stars possible. In every case, the door is closed. Neutron stars do not reignite. White dwarfs do not reignite on their own. Black holes do not release their mass back into the universe on timescales that matter for stellar evolution. Each death is a permanent conversion of active stellar material into a locked-away remnant. There is something profound in recognizing the asymmetry here. Birth and death are not symmetric processes in the lives of stars. A star can be born anywhere that a molecular cloud achieves sufficient density, given the right initial conditions, and its birth scatters light and energy across its surroundings for millions or billions or trillions of years. But its death produces an object that contributes nothing. The remnant is not a source, it is a sink. It receives heat from the surrounding universe in the form of the cosmic microwave background radiation for now, and slowly radiates its own residual heat outward. But the net effect over any cosmologically significant timescale is that each stellar death removes a body from the active account and deposits it permanently in a closed account from which nothing can be withdrawn. The universe is in the business of transferring matter and energy from the active stellar population to the locked-away remnant population, and this transfer runs in only one direction. The three populations of stellar remnants, neutron stars, white dwarfs, and black holes are growing. They have been growing since the first stars died. They will continue to grow as more and more stars exhaust their fuel and die. And the active stellar population, the stars that are currently burning, currently illuminating the universe, currently doing the work that makes the cosmos interesting, is shrinking, not quickly by human standards. The change is imperceptible on the scale of a civilization or even a species, but on cosmological timescales, the trajectory is perfectly clear. Every century adds new stellar remnants to the universe. Every century removes stars from the active population. The direction of travel does not change. The universe is consuming its starlight, one star at a time, and storing the ashes in the dark. Compounding this accumulation of dead remnants is the fact that the remnants themselves cannot be easily reactivated even when they exist in proximity to fresh gas. A white dwarf sitting in a region of the interstellar medium rich in hydrogen gas will accrete that material very slowly, and the accretion-driven nova outbursts that briefly reignite surface fusion are not net sources of new long-term starlight. They consume a small amount of the accreted hydrogen in a rapid surface explosion and return to quiescence, no closer to sustained fusion than before. A neutron star, even more compact and extreme than a white dwarf, can accrete material from a companion and produce X-ray bursts, but again these are brief, surface-level events that do not represent a genuine return to stellar life. The underlying remnant object never changes its fundamental nature. A white dwarf remains a cooling carbon-oxygen or helium crystal. A neutron star remains a degenerate ball of neutrons. A black hole remains a black hole. The only exceptions, type Ia supernovae, driven by a white dwarf crossing the Chandrasekhar limit, or neutron star mergers, are not revivals, but further destructions, converting one type of inert remnant into either dispersed heavy element-rich gas or a new black hole. Each pathway through the stellar remnant landscape moves in the direction of greater inertness, greater isolation, and greater inaccessibility to any future stellar cycle. There is also a structural fact about the universe at large that amplifies the local mechanics of individual stellar death. The gas available for star formation is not uniformly distributed across the cosmos. It is concentrated within galaxies, and galaxies are concentrated within gravitationally bound groups and clusters. The Milky Way belongs to the local group, a collection of roughly 60 galaxies, most of them dwarf galaxies gravitationally bound within a volume of space roughly 10 million light-years across. The local group's gas supply is shared among its member galaxies, and the supply is finite. As star formation proceeds in the Milky Way and Andromeda, the two dominant galaxies of the local group, and as both galaxies are destined to merge into a single merged system called Milkdromeda in roughly 4 to 5 billion years from now, the combined pool of star-forming gas will gradually be consumed by successive generations of stellar births and deaths until the merged system has used up its available supply and star formation within our gravitational neighborhood ends permanently. Regardless of what is happening in the rest of the observable universe, the local group is its own closed system for practical purposes. The gas it has is the gas it will ever have. When that gas is gone, so are the stars. What makes this still more complete in its finality is the context in which these stellar deaths are occurring. These deaths are not happening inside a universe that can easily build new stars from the remnants and recycle the gas. They are happening inside a universe that is simultaneously pulling itself apart on scales larger than galaxy clusters, separating entire galactic neighborhoods from one another at velocities that exceed the speed of light, permanently removing the raw material and the stellar populations of distant galaxies from any possible future interaction with what remains in the local group. The mechanics of individual stellar death are only part of the story. The other part, the mechanism that ensures the isolation, is not just a local phenomenon, but a total and cosmic one, is accelerating across every scale of the observable universe simultaneously. And the scale at which that isolation operates, and the speed at which it is already operating turns out to be far more advanced than most people realize. There is a fact about the universe that most people have never been told, and it changes everything about how the night sky should be understood, and everything about what the concept of stellar death truly means at the largest possible scales of cosmic structure. Right now, at this moment, as you listen to these words, approximately 94% of all the galaxies in the observable universe are receding away from us faster than light can travel. Not because those galaxies are moving through space at superluminal speeds. Einstein's special relativity forbids that, and nothing in this story violates it. Rather, the space between us and those galaxies is itself expanding, stretching the distance at a rate that adds up across hundreds of millions and billions of light years to something that far exceeds the speed of light as a cumulative recession velocity. The galaxies are not breaking any rules. Space is simply growing faster than any signal traveling at light speed can cross it. And this means that 94% of what you can see tonight, every galaxy in that direction, and that direction, and that direction is already permanently beyond the reach of anything or anyone that will ever exist in the Milky Way's future. The light from those galaxies is still arriving, but the galaxies themselves, as they exist now, are gone. They crossed the cosmic event horizon and kept going. The cosmic event horizon is not a wall. It is not a place. It is a distance, currently approximately 16 billion light-years from Earth, beyond which any signal sent today will never arrive at its destination, because the space between sender and target is expanding faster than the signal can travel. Galaxies beyond this line are not merely far away in the ordinary sense. They are causally disconnected from us in a permanent and irreversible way. No telescope can reach them. No radio transmission can reach them. No future technology, regardless of how sophisticated, can bridge the gap, because the gap grows faster than any bridge can be built. Objects within 16 billion light-years can still, in principle, be reached if we sent a signal today. Objects beyond it cannot, even in infinite time, and because the cosmic expansion is confirmed to be accelerating, reaffirmed as recently as June 2026 in a study published in Monthly Notices of the Royal Astronomical Society by a team led by the University of Southampton, which directly tested and refuted claims that the acceleration might be an observational illusion. The horizon is not shrinking toward us. Every year, additional galaxies cross this boundary and join the 94%. What this means in practice is that the universe has already sealed the fate of the overwhelming majority of its own material. Those 2 trillion galaxies visible in the observable universe, each containing hundreds of billions of stars, each surrounded by the remnants of previous stellar generations, each sitting at the center of a dark matter halo extending hundreds of thousands of light years in every direction. Most of them are already unreachable. We can study them with light that left them billions of years ago. We will never be able to touch them, communicate with them, receive a message from them that they sent after a certain point in their history, or do anything whatsoever to alter what happens inside them. They are, for every meaningful purpose, separate universes, and they are receding farther away with every passing second, their recession velocities increasing as dark energy continues its work, deepening the isolation that the geometry of cosmic expansion has already established. The nature of dark energy itself is, as of mid-2026, one of the most actively contested questions in cosmology. The standard model of cosmology, lambda cold dark matter, treats dark energy as a cosmological constant, an energy inherent to empty space that does not dilute as space expands and therefore drives an acceleration that grows stronger over time as more space is created. Under this model, the cosmic event horizon sits at a fixed comoving distance, and galaxies simply cross it as they recede, while the horizon stays stationary relative to the expanding background. The acceleration is eternal, the isolation deepening without limit, until only the gravitationally bound local group of galaxies remains within our permanent reach, an island of matter in an otherwise expanding void. This is the model that the June 2026 Southampton study reaffirmed, showing that claims from a 2025 analysis, suggesting the acceleration was an artifact of stellar age. Miscalculation were themselves based on an error. The acceleration is real. The dark energy is there. Under lambda cold dark matter, it is not going anywhere. But there is a second possibility, actively being investigated by the Dark Energy Spectroscopic Instrument known as DESI, which has published increasingly suggestive findings through its first and second data releases. DESI's DR2 results, published in early 2025, show a preference at 4.2 sigma significance for dark energy that evolves over time rather than remaining a fixed cosmological constant. This is not yet confirmed. 5 sigma is the conventional threshold for a discovery claim in physics, and the same dataset has been interpreted differently by different research groups. A separate analysis published alongside DESI's findings by a team from the Tata Institute of Fundamental Research and the University of Oxford questioned some of the evidence. But the signal is strong enough that cosmologists cannot ignore it, and it raises a question with direct consequences for the timeline of cosmic isolation. What if dark energy is weakening? If dark energy is not a cosmological constant, but rather a dynamic field, something physicists call quintessence, that has been gradually losing energy density over cosmic time, then the rate of cosmic acceleration may eventually slow. Under some models, the weakening could be significant enough that the current acceleration asymptotically approaches a constant expansion rate, rather than continuing to accelerate indefinitely. This would change the long-term horizon structure. A constant but non-accelerating expansion would eventually allow light signals to reach destinations that an accelerating expansion would have cut off permanently. The island of isolation that dark energy is building might be somewhat less complete than lambda cold dark matter predicts. The distinction matters enormously for the very far future of the cosmos. But here is the crucial point, and it must not be obscured by the uncertainty. Whether dark energy is constant or weakening, the separation is already catastrophically advanced. Even if dark energy weakens significantly from this point forward, the 94% of galaxies already beyond the reachability limit are not coming back. The recession velocities are too high, the distance is too great, the accumulated expansion of the past billions of years too irreversible. No realistic scenario for evolving dark energy returns the trillions of already inaccessible galaxies to contact with the local group. The debate between constant and evolving dark energy is a debate about whether our ultimate cosmic island will be slightly larger or slightly smaller, not about whether the island exists. It exists. The isolation has already happened to 94% of everything we can see. This isolation is not merely an abstract cosmological fact. It has a direct consequence for stellar populations across the universe, because it means that each galaxy, each gravitationally bound system of stars, is on its own. Any star that runs out of fuel in a galaxy already beyond the cosmic event horizon runs out of fuel permanently, with no possibility that the heavy elements it contributed to its local interstellar medium will ever be recycled into stars that contribute to any other galaxy. The universe is not a single system undergoing a single long process of stellar evolution. It is, already, a vast collection of isolated systems, each burning through its own local supply of hydrogen, each accumulating its own local population of stellar remnants, each proceeding toward its own local version of stellar extinction, entirely independently of every other system separated from it by dark energy's expanding gulf. The universe's long-term stellar fate does not happen once. It happens 2 trillion times simultaneously and independently in 2 trillion separate gravitational islands, each sealed off from the others. Within our own local group, the gravitationally bound collection of roughly 60 galaxies dominated by the Milky Way and the Andromeda Galaxy, the situation is different. Gravity holds these systems together despite the cosmic expansion, and because the local group is gravitationally bound as a whole, it will not be pulled apart by dark energy. The galaxies of the local group are not receding from each other. They are, in several cases, actively approaching each other. The Andromeda Galaxy, 2.5 million light-years away and approaching at approximately 110 kilometers per second, is the most significant example. Andromeda and the Milky Way are on a confirmed collision course. The timing of their eventual merger remains genuinely uncertain. Updated 3-dimensional motion measurements incorporating data from the Gaia spacecraft suggest it may occur anywhere from 4 to 10 or more billion years from now, but the merger itself is considered essentially inevitable. When it occurs, the 2 spirals will pass through each other multiple times in a gravitational dance that scatters stars into extended tidal streams, triggers explosive bursts of star formation as gas clouds collide and compress, and ultimately fuses both galactic cores into a single elliptical-shaped remnant that astronomers have named Milkdromeda. The merger of the Milky Way and Andromeda is not a collision in the sense of a catastrophic smash-up, because stars are so sparsely distributed that direct stellar collisions during the merger will be extremely rare. But the gravitational chaos of 2 galactic mass systems interpenetrating will dramatically disrupt stellar orbits. Some stars will be flung outward in tidal tails. Some will be scattered into extended halo orbits far from the merged galactic center. A small fraction may even be ejected entirely from the combined system, sent racing into the intergalactic void as hypervelocity stars. The supermassive black holes at the centers of both galaxies, Sagittarius A star in the Milky Way at approximately 4 million solar masses, and the Andromeda Galaxy's central black hole at tens of millions of solar masses, will spiral toward each other and eventually merge in an event that releases gravitational waves detectable in principle across enormous distances. The merged Milkdromeda black hole will be among the most massive objects in the local group. What happens inside Milkdromeda over the hundreds of billions of years following the merger is a story of gradual depletion. The starburst episodes triggered by the merger, those intense periods when colliding gas clouds collapse rapidly into new stars, will consume significant fractions of the available gas supply in a short time. The merger does not create new gas. It merely compresses what already exists, converting it into stars on an accelerated schedule. Once those starburst episodes subside, star formation settles back into a quieter regime and then continues to decline as the gas reservoir empties. The merger of the Milky Way and Andromeda will briefly make Milkdromeda brighter and more productive, but the net effect over longer timescales is to hasten the consumption of the remaining gas supply. The starburst is not a renewal. It is an advance on a budget that was already diminishing. Meanwhile, outside the local group, the rest of the observable universe has already passed beyond the point of return. The Virgo cluster, the nearest major galaxy cluster at roughly 55 million light-years, contains more than 1,000 galaxies, and even this relatively nearby structure is on a trajectory toward permanent inaccessibility. It will cross the reachability limit, the point beyond which even a light signal sent today could never catch up in roughly 100 billion years. The great supercluster complexes, visible across the cosmos, are already beyond the event horizon in terms of reachability for anything except already traveling light. In every direction, the observable universe is a museum of things that will eventually become invisible. As the expansion stretches their light to wavelengths too long to detect, and their distances grow too vast for even future generations of photons to bridge. The redshifting of light from distant galaxies is itself a process with an endpoint. As a galaxy recedes, and its light is stretched to longer and longer wavelengths, the light shifts from visible to infrared, to microwave, to radio, to wavelengths so long they become undetectable with any conceivable instrument. The galaxy does not disappear. It is still there, still burning, still existing, but its signal is stretched past the threshold of detectability. It fades from the universe's sensory landscape not by ceasing to emit, but by emitting at wavelengths too low in energy to do anything useful when they arrive. The final photons from already distant galaxies are arriving at Earth right now, and the galaxies that emitted them will never emit light we can receive again. Every moment that passes locks more of the cosmos into this silent inaccessibility. Consider what this means for the possibility of knowledge about the universe beyond the local group. Every piece of cosmological information that humanity has ever gathered, the Hubble expansion, the cosmic microwave background, the distribution of galaxy clusters, the large-scale structure of cosmic filaments and voids, the existence of dark energy itself, was derived from light that successfully crossed the expanding gulf between distant objects and our telescopes. That crossing happened because those photons were already in transit when the universe was younger and less expanded, and because many of the distances involved, while vast, were still within the range where light could outpace the recession velocity. But for objects already beyond the cosmic event horizon, the 94% no new information is arriving. Whatever those galaxies are doing right now, we will never know. Whatever stars they are forming or extinguishing, whatever collisions are reshaping their structures, whatever exotic phenomena might be occurring in their exotic environments. All of it is happening in complete observational secrecy, permanently screened from any observer in the local group by the geometry of an accelerating cosmos. This is not a limitation that better technology can overcome. It is not that our telescopes are insufficiently sensitive or our detectors insufficiently refined. The information is not present in the universe we inhabit. The photons carrying it will never arrive. The observations are impossible, not because of engineering, but because of physics, and no revision of physics consistent with the evidence is expected to change this. The unreachability of 94% of the observable universe is not a gap in our knowledge that future generations will fill. It is a fundamental, structural feature of a cosmos governed by accelerating expansion, and it is permanent. There is another aspect of cosmic isolation that operates not at the scale of galaxy clusters, but at the scale of individual stellar systems. And it is worth examining because it reveals that the loneliness built into the far future of the cosmos is not merely a large-scale phenomenon. Stars within galaxies are separated from each other by distances measured in light-years, typically 4 to 5 light-years between neighbors in our region of the Milky Way. The nearest star to the Sun, Proxima Centauri, is approximately 4¼ light-years away, which means that a signal traveling at the speed of light takes more than 4 years to make the one-way trip. In the degenerate era, when the remaining stellar population consists entirely of white dwarfs and neutron stars spread through a galaxy whose total number of objects is diminishing through dynamical ejection, these separations will be even larger. Objects scattered into the intergalactic medium during dynamical relaxation will drift through a void where the nearest neighbor is thousands or millions of light-years away and growing farther with each passing eon. Each remnant will be, in the most complete physical sense, alone, not merely distant from its neighbors but receding from them faster than any signal could bridge the growing gap, locked into a trajectory of increasing isolation by both the dynamics of gravitational ejection and the continued expansion of the cosmic background. The role that dark energy plays in this story is not simply to act as the mechanism of separation. It also determines the energy budget of the far future universe. Dark energy, under the standard cosmological constant model, maintains a constant energy density as space expands, which means that as the volume of the universe grows, the total energy contained in dark energy grows with it. This is counterintuitive and has no analog in everyday physics, a form of energy that increases its total amount as the space it fills expands. The source of this energy, whether it genuinely represents the quantum vacuum energy of empty space, or some scalar field that mimics such energy, or something else entirely, remains one of the deepest unresolved problems in fundamental physics. What is observationally established is that this energy drives the expansion, and that its effects are real and measurable, confirmed by multiple independent lines of evidence, including Type Ia supernovae, baryon acoustic oscillations, the cosmic microwave background power spectrum, and the large-scale structure of the galaxy distribution. The June 2026 reaffirmation of accelerating expansion, which rebutted a 2025 claim of a slowdown, adds further confidence to this observational foundation. If dark energy is a cosmological constant, it represents, in a sense, the universe's permanent operating budget for expansion energy that cannot be converted into any other form, energy that does not dissipate, energy that simply continues driving space apart forever. The stellar material, the gas, the radiation, the gravitational potential energy of structures, all of these forms of energy are subject to dissipation, conversion, and eventual degradation into the uniform thermal noise of heat death. But the dark energy, if truly a cosmological constant, persists. It is the one form of energy in the universe that will still be present when everything else has been leveled into uniformity. In the heat-death universe, dark energy is still there, still driving the expansion, still adding volume to an already infinite void. But with no temperature gradients left to exploit, with no free energy left to convert to work, with nothing left to be structured or complexified or organized, the dark energy's presence is cosmologically inert. It expands a space that has nothing in it worth expanding. It is the universe's last ongoing process, the continued growth of an empty room. The cosmic microwave background radiation, the faint afterglow of the Big Bang itself, the universe's oldest detectable light, provides an indirect measure of the isolation process in action. Currently, it fills all of space at a temperature of approximately 4.9 degrees Fahrenheit above absolute zero. As the universe continues to expand, this background radiation will be stretched to longer wavelengths and lower temperatures. In the far future, the cosmic microwave background will have cooled to temperatures measured in fractions of a degree above absolute zero, and its photons will be stretched to wavelengths so long they will carry effectively no energy and will be detectable by nothing. The afterglow of the Big Bang will become, in practice, invisible, the last independent evidence that the universe had a beginning, that there was a moment of extreme heat and density from which everything expanded, will be erased from the observable record. Any civilization arising in Milky billions of years hence, after the cosmic microwave background has cooled below the threshold of detection, will find themselves inside a single, isolated, slowly dimming island of stars with no surrounding context, no neighboring galaxies visible, no relic radiation marking the origin of the cosmos. They will be, in every observational sense, alone. This is a profound epistemic consequence of cosmic isolation. The evidence for the universe's history is being destroyed by the very processes that constitute that history. Dark energy expands the space through which the cosmic microwave background photons travel, stretching them toward invisibility. The recession of distant galaxies removes them from observational range. The aging of stellar populations within galaxies slowly converts the bright record of nucleosynthesis into cold, dark stellar remnants. The universe is erasing its own autobiography as it writes it, and the erasing catches up to the writing faster and faster as expansion accelerates and stellar populations age. A civilization of sufficient technological sophistication that arose in the Milky Way today has access to an extraordinary archive. 2 trillion visible galaxies, the cosmic microwave background, the chemical record encoded in stellar spectra, the gravitational wave background from black hole mergers, a wealth of evidence for what the universe was and where it came from. A civilization arising in Milky Way 100 billion years from now will have a fraction of this information, and a civilization arising 1 trillion years from now will have almost none of it. The universe is moving toward a state in which its own history is unrecoverable, and it does so with no mechanism for reversal, no possibility of reconstruction. The mechanism of dark energy isolation also produces a striking asymmetry between the past and future of cosmic visibility. Right now, looking outward in any direction, we receive light that departed from extremely distant galaxies billions of years ago, when those galaxies were much closer to us because the universe was smaller then and the distances were shorter. The light was able to begin its journey in conditions under which it could eventually reach us. But light emitted by those same galaxies today, or at any point after their recession velocity exceeded the speed of light, will never reach us. We are therefore in a unique observational position. We can see the past of things we can no longer reach, but we cannot see their present. The galaxies in the Hubble ultra-deep field, some of them 13 billion light-years away, existed in forms visible to us. The same galaxies today are completely beyond observational contact. We are looking at memories of things that have, for all practical purposes, already ceased to be part of our universe. The Virgo cluster, containing over 1,000 galaxies and sitting approximately 55 million light-years away, will serve as the nearest major external gravitational system for some billions of years. But even the Virgo cluster, relatively close by extragalactic standards, is not gravitationally bound to the local group. It is a separate structure, and dark energy is steadily increasing the distance between it and us. In roughly 100 billion years, light emitted by the Virgo cluster today will still be reaching us. We will still be observing it, still studying it. But a light signal sent from within the local group at that future date will no longer be able to catch up to Virgo's recession. The last moment at which we could, in principle, have sent a probe to the Virgo cluster at the speed of light and expected it to arrive already past some billions of years ago. The cluster is still visible. It is already unreachable. This gap between visibility and reachability is one of the strangest features of a dark energy-dominated cosmos, and it represents the universe in the process of dismantling the very connections that once made it a single coherent entity rather than a collection of sealed, separated vaults of matter, each burning through its own allotted supply of fuel, in the permanent company of nothing outside itself. The isolation is the story. The mechanics of how individual stars die, covered in Part 2, determine what the remnants look like. The accelerating expansion of dark energy determines that those remnants are sealed into separate, unreachable cosmic islands. Together, these two processes, stellar exhaustion and cosmic separation, ensure that the universe's long-term future is not just dark, but fundamentally, structurally, irreversibly alone. And the most important thing about this isolation, the thing that makes it unlike anything in ordinary human experience of separation, is that it cannot be reversed by waiting. Every year that passes makes the isolated fraction larger, not smaller. Every year locks more of the observable universe into the permanent beyond. The clock of cosmic isolation runs in only one direction, and it has been running since dark energy began to dominate the universe's energy budget approximately 4 billion years ago. The direction it runs toward is a subject that belongs to our topic later on in this video. The era in which even the last stars of the local group have exhausted their fuel, the stellar remnants have begun their own long cooling, and the only structures left in the universe are the very things that cosmic physics built as the final monuments to what burning once was. This is the mechanism by which isolation operates on the grandest scale, not through any active process that reaches out and seizes galaxies, but through the relentless geometry of accelerating expansion that simply keeps growing faster than light, creating more and more unreachable space between every gravitationally unbound system in the cosmos. Dark energy does not push galaxies away from each other the way a physical force pushes objects. It is more subtle and more total than that. It is embedded in space itself, expanding the medium through which everything moves, so that the distance between unbound systems grows, not because anything is being pushed, but because the ruler being used to measure the distance is itself getting longer. There is no edge to push against. There is no center that is expanding outward. Every location in the universe experiences the same expansion, and every location is simultaneously the center of the same horizon, beyond which the same 94% of everything has already passed. The stars of the universe are dying in isolation, not metaphorically, literally. Each galaxy, each stellar population, each red dwarf burning away its last reserves of hydrogen is doing so completely cut off from the rest of the cosmos that has already passed beyond the horizon. The death of every star in a distant galaxy is an entirely private event. Its light, the last gasp of a fusion process that ran out of fuel, travels outward for billions of years through an expanding medium and arrives at whatever observers might exist as a whisper of ancient history, the record of something that was already finished by the time the signal departed. The star itself, long cold and dark by the time its deathlight reaches anything, is not witnessed. It is merely remembered, incompletely, in red-shifted photons that carry less and less information with every passing era. The isolation is the story. The mechanics of how individual stars die, covered in Part 2, determine what the remnants look like. The accelerating expansion of dark energy determines that those remnants are sealed into separate, unreachable cosmic islands. Together, these two processes, stellar exhaustion and cosmic separation, ensure that the universe's long-term future is not just dark, but fundamentally, structurally, irreversibly alone. And the most important thing about this isolation, the thing that makes it unlike anything in ordinary human experience of separation, is that it cannot be reversed by waiting. Every year that passes makes the isolated fraction larger, not smaller. Every year locks more of the observable universe into the permanent beyond. The clock of cosmic isolation runs in only one direction, and it has been running since dark energy began to dominate the universe's energy budget approximately 4 billion years ago. The stars dying in those sealed-away galaxies are dying without witnesses. They collapse, they explode, they cool and go dark, in a cosmic privacy so complete that not a single photon from those final events will ever reach the local group in any future we can compute. Each extinction is total and unacknowledged. And in the deep future of the local group itself, after the Milky Way and Andromeda have merged into Milkdromeda, after the last external galaxies have crossed the horizon, after the cosmic microwave background has cooled past detection, the same process of slow stellar exhaustion that has been operating on every one of those sealed-away islands will begin its final chapter here at home, in the very last gravitationally bound structure remaining within the reach of anything that once burned in this universe. The universe will not end with a bang. It will not end with a dramatic final explosion, a collapse into a singularity, or any moment of concentrated catastrophe that could be marked on a calendar or witnessed in a single night. The universe's ending is not a moment. It is a process, extraordinarily slow by any standard, that began the instant the first star ignited and will not reach its final stage until timescales so vast that the numbers used to express them become essentially meaningless to human intuition. What lies at the end of that process is a state, a condition of the universe rather than an event. And understanding that state, how it comes to be, and what it means for everything that once burned and lit and moved, requires walking deliberately through the eras that follow the Stelliferous Era, the degenerate era, the black hole era, and the terminal state of maximum entropy that physics calls heat death. Begin with what happens to the local group when the Stelliferous Era ends, not in our immediate cosmic neighborhood, which has several trillion years of red dwarf burning ahead of it, but in the sense of the era's conclusion across all the isolated cosmic islands that dark energy has sealed off from each other. In each of those islands, some version of the same process plays out. Stars form, burn, die, leaving white dwarfs, neutron stars, and black holes. The gas supply dwindles. Star formation slows. Eventually, in each island independently, the last molecular cloud collapses, the last protostar ignites, and the last new sun begins its fusion clock. No more new stars will ever form in that island again. This moment, different for different islands, depending on their individual gas supplies and star formation histories, marks the end of the Stelliferous Era for that system and the beginning of the Degenerate Era. For the merged Milky-Way galaxy, models suggest this transition will occur sometime in the range of 100 trillion years from now, roughly 7,000 times the current age of the universe. In the period leading up to it, the stellar population shifts progressively toward the most patient stars. The massive stars and sun-like stars exhaust their fuel and convert to remnants across timescales of millions to tens of billions of years. The intermediate mass red dwarfs go dark over hundreds of billions of years. What remains, burning longest, are the dimmest and least massive red dwarfs, the ones with roughly 1/10 the mass of the Sun, consuming their fuel at such a miserly rate that they will still be generating light from nuclear fusion when the universe is approximately 1,000 times its current age. These are the universe's last fires. They burn slowly, dimly, patiently, in a sky that has already lost every galaxy except the merged remnants of the local group, in a cosmos that has already stretched the cosmic microwave background to invisibility, in a universe that will never again form a new star from a newly collapsing cloud. They burn because they started 1 trillion years ago, and the physics of low-mass stellar fusion is patient enough to let them keep going. But patient is not the same as endless. The Degenerate Era is the phase that follows the final red dwarf. Its name refers not to moral decay but to the physics of degenerate matter, the quantum mechanical state in which white dwarfs and neutron stars exist, supported against gravitational collapse, not by thermal pressure from ongoing reactions, but by the Pauli exclusion principle, the quantum rule that forbids two fermions from occupying the same quantum state. White dwarfs are electron degenerate. Neutron stars are neutron degenerate. Both types of object can, in principle, persist for an extraordinarily long time because degenerate matter does not require ongoing reactions to maintain its structure. It simply is. It holds itself up with quantum mechanics rather than heat. It requires no fuel. But holding itself up is not the same as being alive. A white dwarf that forms from the death of a red dwarf at the very end of the Stelliferous Era will, at the moment of its formation, be composed primarily of helium, the ash of the red dwarf's long, patient hydrogen fusion at a temperature of many thousands of degrees Fahrenheit, glowing dimly in the ultraviolet. Over the following hundreds of billions of years, it will radiate that stored thermal energy into space, cooling slowly. Its surface will shift from blue-white to yellow-white to pale orange to the dull red of a dying ember. The cooling rate declines as the temperature falls because cooler objects radiate less efficiently, so the final stages of cooling take longer than the earlier ones. The timescale for a white dwarf to cool completely to a black dwarf, a temperature indistinguishable from the cosmic background, is theoretically longer than the current age of the universe by factors of many billions. The universe is too young right now for any black dwarf to exist. Every white dwarf that has ever formed is still emitting some detectable radiation, but the direction is fixed. They are all cooling. Not one of them is warming. The universe is building, with extraordinary patience, a population of cooling cinders, and the cooling is irreversible and permanent. What does the Degenerate Era actually look like from inside? Consider the sky over Milky-Way 10 trillion years from now. Star formation ended trillions of years ago. The galaxy contains no nebulae, no glowing stellar nurseries, no blue supergiants blazing through clouds of ionized gas. What it contains is a large population of white dwarfs at various stages of their cooling sequence, their surfaces ranging from the still warm glow of objects that formed hundreds of billions of years ago to the nearly invisible chill of the oldest and coldest. It contains a smaller population of neutron stars, also slowly cooling, but from much higher initial temperatures and with different cooling physics, mostly invisible at radio wavelengths, except for the few that still spin rapidly enough to produce detectable pulsed emission. It contains an assortment of black holes of various masses, from the stellar mass remnants of the most massive ancient stars to the merged supermassive black hole at the galactic center, which has grown enormously over the intervening trillions of years by accreting whatever stray gas and stellar remnants happen to cross its path. The degenerate era is also the era in which the thermodynamic arrow of time, always present but often masked by the activity of stellar burning, becomes the dominant fact of the universe's experience. Every process happening in the degenerate era, white dwarf cooling, neutron star spin down, the slow gravitational scattering of stellar remnants, is a process that increases entropy. None of them are reversible. None of them are refueled or reset. The white dwarf that cools from 10,000 degrees Fahrenheit to 9,000 degrees Fahrenheit to 8,000 will never warm back up. The neutron star that slows its rotation from 100 revolutions per second to 99 will never accelerate. The system of white dwarfs, drifting slowly apart through gravitational interactions, will never reassemble itself into a structured galaxy. Every process in the degenerate era moves in one direction, toward greater disorder, less structure, less usable energy, lower temperature, greater uniformity. The degenerate era is the universe practicing for heat death, running through the final slow movements of a symphony that is clearly ending, each note quieter than the last, each phrase stretched across timescales that dwarf the entire preceding history of stellar activity. Throughout this degenerate era, another process is operating quietly on the population of stellar remnants. Gravitational interactions. Every object in the galaxy is moving, and the gravitational influence of one object on all others, though weak at the typical separations involved, accumulates over very long timescales. Through a process called dynamical relaxation, the gradual exchange of kinetic energy between objects through gravitational encounters, stellar remnants slowly redistribute their orbital energies. Lighter objects tend to gain velocity over time. Heavier objects tend to slow down and sink toward the center. The statistical mechanics of this process, operating over timescales of approximately 10 to the 19th years, leads to a predicted endpoint. Most of the stellar remnants in Milky Way are gradually ejected from the galaxy entirely, flung into intergalactic space through the accumulation of gravitational perturbations, while a small fraction fall inward toward the central black hole and are consumed. The galaxy does not hold its contents forever. Gravity, operating patiently over enough time, disperses them. This is a subtle point worth pausing on. The galaxies of the universe are commonly thought of as permanent structures, things that, once formed, persist essentially forever. But permanence in astronomy is always relative to timescale, and on the timescale of dynamical relaxation, galaxies are not permanent at all. They are temporary aggregations of matter, held together by gravity, but slowly leaking their contents into the intergalactic medium through the statistical mechanics of long-term gravitational interaction. Over a period of approximately 10 to the 19th years after the end of the Stelliferous Era, a timescale roughly 1 billion times longer than the current age of the universe. The population of white dwarfs, neutron stars, and stellar mass black holes that makes up the remnant Milky Way will be largely dispersed. They will drift individually through an expanding void, separated from each other by distances that grow with the continued expansion of space, cooling as they go, carrying no fuel, doing no work, emitting no light except the faint and ever-diminishing radiation of stored thermal energy. What remains in the center of the dispersed galaxy, after the vast majority of its stellar remnants have been scattered into intergalactic space, is the supermassive black hole, or more precisely, what was once the central black hole, grown massive over trillions of years of accretion. This object is the last major concentrated mass in the local cosmic environment, and for a very long time, on timescales measured in tens of trillions of years, it is simply there, sitting at the center of what was once a galaxy, now a void, surrounded by nothing close enough to accrete. It is not shrinking. It is not radiating at any detectable rate given the current state of the universe. But it is not permanent either, and the mechanism of its eventual destruction is one of the most remarkable and consequential predictions in all of theoretical physics. In 1974, the physicist Stephen Hawking derived, from the intersection of quantum field theory and general relativity, that black holes are not completely black. The event horizon, the surface of no return, interacts with quantum fields in the vacuum of space in a way that causes the black hole to emit a faint but steady thermal radiation, now called Hawking radiation. The mechanism is deeply quantum mechanical. Near the event horizon, the curvature of space-time affects the behavior of quantum fields in a way that results in the creation of particles that carry energy away from the black hole. Over time, this process removes energy, and therefore mass from the black hole. It slowly evaporates. The rate of evaporation is inversely proportional to the mass of the black hole. Smaller black holes are hotter and evaporate faster. Larger black holes are colder and evaporate more slowly. The Hawking temperature of a stellar mass black hole is approximately 10 to the -8 degrees Fahrenheit above absolute zero, far colder than the current cosmic microwave background, which means that for now, such a black hole absorbs more background radiation than it emits and is actually accreting, not evaporating. But as the universe continues to cool and the cosmic microwave background temperature drops below the Hawking temperature of even stellar mass black holes, the evaporation begins. And once it begins, it runs to completion. For a black hole with the mass of the Sun, the evaporation timescale is approximately 10 to the 67 years. This is not a typo. 10 to the 67th power years. The current age of the universe is approximately 10 to the 10th power years. The ratio between these two timescales is 10 to the 57th, a number so large that multiplying the current age of the universe by the number of atoms in the observable universe does not approach it. A stellar mass black hole will sit essentially unchanged for a timescale that makes the entire history of stellar evolution, from the first star to the last red dwarf, look instantaneous by comparison. And then, after all that time, it will begin to lose mass perceptibly, and as it loses mass, its Hawking temperature will rise, and as its temperature rises, it will evaporate faster, in a runaway process that accelerates dramatically toward the end, culminating in a final burst of high-energy radiation as the black hole shrinks below a critical mass and completes its evaporation in a flash of gamma rays that briefly illuminate nothing. For the supermassive black holes at the centers of galaxies, objects millions to billions of times, the mass of the Sun The evaporation timescale scales with the cube of the mass. A black hole of 100 billion solar masses evaporates in approximately 2 times 10 to the 100th years. Even larger black holes formed from the merger of galaxy clusters may take up to 10 to the 106th years. These are numbers for which human language has no meaningful vocabulary. They are timescales on which everything else that has ever happened in the universe is a single brief opening act. The stars burned, the galaxies collided, the white dwarfs cooled, the stellar remnants dispersed. All of this occurs in the first few moments of the black hole era, cosmologically speaking, before the dominant business of this last active epoch in the universe's history, the slow quantum evaporation of its last massive objects, even begins in earnest. There is also, somewhere in this timeline, the question of proton decay. The proton, the positively charged particle at the heart of every atomic nucleus, the building block of ordinary matter, is, according to the standard model of particle physics, a stable particle. In everyday experience, and in all experiments conducted to date, protons do not decay. They exist indefinitely. But many extensions of the standard model, including various grand unified theories that attempt to combine the strong, weak, and electromagnetic forces into a single framework, predict that protons are not actually stable on the longest timescales. Under these theoretical models, a proton left to itself in isolation for approximately 10 to the 34th to 10 to the 42nd years will eventually decay into lighter particles, typically a positron and a neutral pion, which itself decays quickly into photons. If protons decay on this timescale, then not only black holes but every ordinary object in the universe, neutron stars, white dwarfs, cold black dwarfs, and any other matter made of protons and neutrons will eventually dissolve into radiation. The baryonic matter of the universe will not persist forever in the form of cold stellar remnants. It will evaporate into photons and leptons on a timescale shorter by many orders of magnitude than the evaporation of a supermassive black hole. Proton decay has not been observed experimentally. Large underground detectors constructed specifically to search for it, including Super Kamiokande in Japan, one of the world's most sensitive proton decay experiments, have watched enormous tanks of water for decades and have not seen a single confirmed proton decay event. This places lower bounds on the proton lifetime, currently pushing the expected lifetime to at least 10 to the 34th years for the most commonly predicted decay channel. But the absence of observed decay does not mean decay is impossible, only that, if it occurs on a timescale longer than current experiments can probe. The question of proton decay is one of the genuinely open questions in fundamental physics, and its resolution will determine whether the stellar remnants of the degenerate era persist as matter for timescales approaching those of black hole evaporation, or whether they dissolve into radiation first. Either way, whether protons decay or persist, the endpoint is the same. The black holes will evaporate through Hawking radiation. The stellar remnants will either dissolve through proton decay or cool to absolute silence. The universe will arrive at a state in which no significant concentrations of energy or matter remain in any organized form. The path to that state may vary in its details depending on whether proton decay is real, but the destination is not changed by either answer. And the nature of the evaporation, the character of these final black hole deaths in the deepest future of the cosmos, deserves attention because it is the loneliest event that physics can describe. A supermassive black hole, spending 10 to the 100th years slowly evaporating, is, in the most technical sense, doing something. It is radiating, it is losing mass, it is producing a trickle of particles that carry its energy away. But this activity is as far from what we ordinarily call an event as anything imaginable. The radiation from a black hole of billions of solar masses is at a temperature so close to absolute zero that it is many billions of times colder than the coldest known objects in the present universe. It radiates so slowly that the entire current age of the universe passes before any perceptible mass is lost. The evaporation is happening in a strict physical sense, but it is happening in a cosmos that has no witnesses, no observers capable of detecting it, no background radiation warm enough to be distinguished from the Hawking signal. The final black holes evaporate in absolute solitude, completing their dissolution in a burst of radiation that no receiver will ever detect, in a universe that has, for all practical purposes, already settled into its terminal state, long before the last black hole is gone. But it does begin, and it does complete. This is the key fact about Hawking radiation. It is not merely a process that makes black holes slightly smaller. It is a process that, given enough time, destroys them entirely. The black hole information paradox, whether the information about what fell into the black hole is preserved in the outgoing radiation or lost, remains one of the deepest unresolved questions in theoretical physics, and its resolution will have profound implications for understanding the nature of quantum gravity. But the evaporation itself is considered theoretically robust, grounded in the same intersection of quantum mechanics and general relativity that produced the entire modern understanding of black hole thermodynamics. The black holes will evaporate. The last one will eventually complete its evaporation in a final burst of particles and radiation. And then there will be no black holes, and there will be no stars, and there will be no white dwarfs radiating their stored heat, and there will be no neutron stars spinning in the dark. There will be nothing with significant structure at all. What remains after the final black hole evaporation is the terminal state that thermodynamics predicted in the 19th century and that modern cosmology confirms: a thin, diffuse, extraordinarily cold gas of photons, electrons, positrons, neutrinos, and a scattering of other stable elementary particles, expanding forever through a space that is itself growing at an accelerating rate. There are no temperature gradients, not small temperature gradients, none at all. Every region of space is at the same infinitesimally small temperature, because everything that could have created a temperature difference has been smoothed away by the inexorable march of entropy. The second law of thermodynamics, which states that entropy in a closed system always increases over time, has been satisfied in the most complete way imaginable. Entropy is at its maximum, and not a single thermodynamic process remains to increase it further. There is no free energy. There is no available work. There is nothing that can happen. The second law is worth dwelling on here, because it is both the engine of the universe's history and the author of its ending, and it is one of the few laws in physics that has an inherent directionality in time. Most fundamental physical laws are time-symmetric. The equations that describe the motion of particles, the propagation of light, the behavior of quantum fields, all of these work identically, whether time runs forward or backward. Nothing in the mathematics of physics itself distinguishes past from future. But entropy, the measure of the number of possible arrangements a system's components could be in, tends to increase as time moves forward. This tendency is not absolute at the microscopic level. Individual random processes could, by chance, momentarily decrease entropy in a tiny region. But In any macroscopic system with a large number of components, the probability of spontaneous entropy decrease is so astronomically small that it is effectively impossible. The universe, containing the largest possible number of components, moves irreversibly toward greater entropy with each interaction, each reaction, each process. This directional movement is what physicists call the arrow of time. It is the reason that broken objects do not spontaneously reassemble themselves, that heat flows from hot regions to cold regions and never spontaneously in reverse, that stars burn their fuel without ever having the ash spontaneously reconstruct itself into fresh hydrogen. The universe is always moving from more ordered to less ordered, from lower entropy to higher entropy, from free energy to dispersed energy. Heat death is simply the end point of this journey, the state where the journey has reached its conclusion because there is no lower entropy condition left to move away from. The profound irony embedded in all of this is that the very processes that made the universe rich and interesting, gravity creating stars, nuclear fusion creating heavy elements, the chemical complexity of matter, enabling planets and biospheres, are all entropy increasing processes. They all consume free energy and degrade it. They all move the universe forward along its one-way path toward equilibrium. The stars that illuminate the cosmos and make it observable and beautiful are themselves the mechanism by which the universe runs down. The nebulae that form in such spectacular colors are gas clouds in the process of collapsing and releasing gravitational potential energy as radiation, increasing entropy. The supernovae that scatter heavy elements and trigger new generations of star formation are explosions that convert one form of ordered energy into dispersed radiation and kinetic energy, increasing entropy. The richness and elaboration and complexity that the Stelliferous Era produces is real and genuine, but it is built entirely on the conversion of free energy to heat, and every instance of that complexity is a step along the path toward the featureless equilibrium of heat death. The universe, in generating stars and galaxies and planets and everything that lives on or around them, is not working against heat death. It is the mechanism of heat death. Burning is how the universe reaches its final stillness, one star at a time. This state is called heat death, and it requires careful explanation because the name is misleading in at least two ways. First, there is no heat in the ordinary sense. The universe, in heat death, is extraordinarily cold, perhaps a tiny fraction of a degree above absolute zero, and even that residual temperature is only present as a theoretical description of the distribution of the remaining particles, not as anything that could warm anything else. Second, it is not death in the sense of a moment of cessation. Heat death is a condition, not an event. It is the state the universe is asymptotically approaching as entropy increases and free energy dissipates, and in principle the approach continues indefinitely without the universe ever quite reaching perfect equilibrium. The heat death is not a wall the universe hits. It is a horizon it approaches without ever completely arriving. But for all practical purposes, for every purpose that involves the possibility of structure, of complexity, of chemistry, of life, of observation, of any process that a physicist might describe as interesting, the universe reaches heat death when its last source of free energy dissipates. And that dissipation happens with the evaporation of the last black hole. What should be understood clearly is that heat death does not mean the universe stops existing. The particles are still there. The space is still there and still growing. The photons are still traveling through it. Their wavelengths, stretched to absurd lengths, by the continued expansion of space, carrying energy so diluted that it would be indistinguishable from pure absence to any instrument conceivable by any mind that ever existed during the Stelliferous Era. But nothing is happening with them that could be described as a process. No reaction occurs, no work is done, no information is processed, no structure forms. No star ignites, no planet coalesces, no chemistry takes place, no biology is conceivable. The universe persists, in some technical sense, as a thin, cold, expanding medium of particles at maximum entropy, and it will do so forever because there is nothing left to end it. There is no collapse, no big rip, no final explosion, just an expanding void of maximum entropy, growing colder as the expansion continues to dilute even the residual particle density forever. This is the truth the entire script has been building toward, and it requires sitting with for a moment without softening it. The Stelliferous Era, all 100 trillion years of it, was real. The light that fills the universe tonight is real. The 400 billion stars of the Milky Way are burning real hydrogen in real nuclear furnaces and filling real space with real photons. The nebulae where new stars are forming are real, and the planets condensing around those stars are real, and the chemistry happening on those planets is real. All of this is actual and present and extraordinary, and it is all, in the long run, temporary. Not in the vague sense that nothing lasts forever, but in a specific, quantifiable, physically grounded sense. The fuel runs out, the remnants cool, the expansion seals off the escape routes, the last free energy dissipates, and the universe settles into a state that it will never leave, because there is nothing left to disturb it. The loneliness that ends the story of every star is not imposed on the universe from outside. It is built into the physics of fusion and entropy and expansion that made the stars possible in the first place. The same laws that lit the universe will, with perfect consistency and no contradiction, extinguish it. This is not despair. It is not meant to be heard as despair. The scale of what burns before the darkness is staggering. 100 trillion years is not nothing, and the structures that form within it, from the first population 3 giant to the last patient red dwarf, from the first rocky world to the last cooling cinder of a planet orbiting a white dwarf, represent an elaboration of physical complexity that the universe appears to have nowhere else to invest. The fact that this elaboration has a conclusion does not diminish what it is. It is worth noting that the total duration of the Stelliferous Era, the window of time during which burning, structured, complex things exist, is greater than any human number system was built to intuitively process. To call 100 trillion years temporary requires first acknowledging that temporary, in this context, means something almost indistinguishable from permanent by any yardstick calibrated to human experience. The temporariness is real in the physics. It does not feel real from inside it. And perhaps that gap between the physical fact of finitude and the experiential enormity of the time available is itself part of what the Stelliferous Era is for. Not for anything, but useful if a concept like usefulness applies at these scales as a reminder that the universe did not merely flash and disappear. It burned with extraordinary abundance, for an extraordinary length of time, before the fuel ran out and the embers cooled. The fact that this elaboration has a conclusion does not diminish what it is. A fire is not less real because it goes out. A star is not less radiant because its fuel ends. The Stelliferous Era, in all its length and light and noise, happened. The loneliness that followed was earned by everything that came before it. and the darkness after the last black hole evaporates is, in its own way, the universe's deepest statement about what it means to have burned at all. That burning was possible, was real, was abundant beyond comprehension, and was, in the end, enough. Rest now, beneath the last light that will ever cross this sky.